Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover domains of multivariable functions. And we're going to take like a calculus 1 to calculus 3 approach, give you something familiar, and then, kind of expand this into multiple dimensions. So if I ask you to determine the domain, like in a pre-calc or a calc 1 class, really a lot of times they ask, where is it continuous for a calculus 1 class? Well, we're really just asking, what's the domain of this function? And we know that we can see that we can't divide by 0. It'll give us something that's undefined. So we know that this is a problem where the denominator is not allowed to be 0. So we'll say the denominator is not allowed to be equal to 0, which means x minus 4 is not allowed to be equal to 0, which means x is not allowed to be 4. Now we can graph this thing's domain. And remember that functions of this type have, inputs which are an x-axis, outputs which are a y-axis. So when I'm graphing the domain of this thing, I'm really just talking about the inputs. So what I can do is I can do an x-axis here, and we know that x is not allowed to be equal to 4, so let's call this spot 4 here. So that means everything except 4 will work. What I mean by that is for x to be in the domain of the function, it must have a real value output. So if I plug in, say, anything over here or anything over here, let's say 5, for instance, this is inside the domain. Well, if you plug in 5, you're going to get a real number back. 5 times 5 is 25. 5 minus 4 is 1. 25 over 1 is 25. You can see that 25 is a real number. It doesn't have to be an integer, any real number. So if you plug in 4.1, you'll still get a real number back, but it'll be, not a whole number this time. Except if you plug in 4, you're going to have 20 over 0, and that's undefined. Now, when we move into calculus 3, we're talking about functions that have input space of 2 dimensions. We have the xy plane as our input space as opposed to this, which is just an x-axis. So when I'm talking about the domain of this function, we'll have an x and a y-axis and talk about, its inputs. Now, this actually has the exact same kind of problem that I have, a division by, something in the denominator that has variables in it. So we know that the denominator is not allowed to be equal to 0. So same exact problem, denominator not allowed to be equal to 0. So x minus y is not allowed to be equal to 0. Now, in your classic calculus 3 class, you'll have functions that tend to be linear or quadratic or, even circular. So a lot of times I tell students, if you can solve it for y and you get a function that's familiar, then go ahead and do that. Now, if you see circles, then, solve it for x squared plus y squared, and then you'll see that circular picture. So I'm going to solve this thing for y. So subtracting x, so negative y is going to be negative x, or I can just send a y to the other side. That'd be faster. So x is not allowed to be equal to y, or I can say, y is not allowed to be equal to x. So instead of this being just a single point on the x-axis, y equals x is actually a curve on this xy plane. But remember, not equals. So when I'm going to do not equals, I'm going to do it as a dotted line. So y is not allowed to be equal to x. So this dotted line is going to represent this open circle, which means every other point in this space will work. It means it's part of the domain. So if I was going to graph its domain, the domain is going to be all this stuff except this dotted line. I'm trying to make it pretty, but no matter what point you grab inside of the shaded region, it's going to give you a real number output. So for instance, if I do something like really easy, what about the point like 1 comma 0? That's inside that space. So 2 times 1 is 2. And then 3 times 0 is 0, so the numerator will be 2. And I'll have 1 minus 0, which is going to be 1. So this will spit out the number 2 over 1, which will give you 2, which is a real number. Now, you can pick any other point in here. It might be, rational. It might be some kind of, yeah. So it doesn't have to be an integer is what I'm trying to say. As long as it's a real number, rational or irrational, we're fine. Okay, so So I picked two examples that are, again, very familiar when it comes to something in precalculus, and then I'm really just extending this into multiple variables into calculus 3. So if I ask you guys to find the domain of a radical, what we know is the way radicals are handed is we say the radicand has to be greater than or equal to 0. The reason why is if we plug in any negative number in here, you're not going to get a real value input. You're going to get something that has an I because you're going to have the square root of -1. So that basically means this radicand has to be greater than or equal to 0. So that means 6 minus 2x has to be greater than or equal to 0. And then we go ahead and solve this thing for x. So negative 2x is greater than or equal to -6. And then divided everything by -2 is going to flip the set to that sign. So this is going to be less than or equal to 3. So again, on the x-axis, let's call this 3. What I know is the domain is going to consist of all values that are going to be less than or equal to 3. So it's going to be closed circle, and then it's going to be all these values. Again, it means that if I plug a number in here and a number from this set into this function, it's going to spit out a real number. Now, if I do the same thing for, say, a calculus 3 problem, this also has a square root. So again, the radicand has to be greater than or equal to 0. So 4 minus x minus y squared is greater than or equal to 0. And now, actually, what I'm going to do, I'm gonna split it up. I want this to be x squared. It's okay. It's okay. Flip it over. So back to, a pre-calculus problem to a calculus 3 problem as far as finding the domain. So in this case, I have picked a function that has a radical in it, and what we know is for the domain that the radicand has to be greater than or equal to 0. Now we know this is because if you plug a negative number under the radical, you're going to have the square root of -1 in there, which means you're going to get an I back, which is not a real number. So we force this radicand to be greater than or equal to 0, so then we get real number outputs. So then we solve it for x. So negative 2x is greater than or equal to -6. Divided by -2 is going to switch the sense of that sign, so this is going to be 3. So if this is our value 3, we know that that domain is going to be less than or equal to that value. So it's going to look like this. Now, again, the domain space of this is just, one variable. That's why this is an x-axis. And similarly, when we have a calculus 3 with a, two variable input, I know that the domain space of this thing is going to be, an xy plane as opposed to just a x-axis. Okay, so very similar problem. The radicand has to be greater than or equal to 0. So then 4 minus x squared minus y has to be greater than or equal to 0. And then again, we're going to go ahead and solve this thing for y because I can see that y doesn't have this any power on it. It's just easy to do so because if I solve it for y, I'm going to get something that's familiar. I'm going to get a function I know how to graph. So minus y is going to be greater or equal to x squared minus 4. And then finally, multiplying both sides by -1 is going to switch the signs of the sign. So y is going to be less than or equal to negative x squared plus 4. So what we know is I know how to graph that, and our equal sign is going to be a solid line. This has an equals bar on it. So when I graph this function, I'm going to graph the solid function. So 1, 2, 3, 4, and it's x squared pointing down, so we know it's this. So the solid means that this is part of the domain. So into this closed point. And then it's going to be less than or equal to it. So it basically means that all the values inside of here are going to be part of the domain. Now, also what that means if you pick a value outside of here, underneath is going to be negative and you'll get i's back. So these are the only spots where you get real numbers as far as outputs for this function. All right, so one more. So our last example will deal with some logarithms. And we know the domain of logarithms would be when its argument is simply greater than 0. Remember that logarithms have this asymptote at x is equal to 0, so it looks like, the Well, it's the inverse of the exponential, so it's going to look like this, where it's got an asymptote of 0. And what this is going to do is this is going to shift that asymptote around. Actually, more importantly, this is quadratic in here, so it's going to be a little more interesting. So let's set that argument greater than or equal to 0. So we're going to have x squared minus 4 is greater than, sorry, simply greater than 0. Now, when I want to graph this thing, it's not really just as easy as factor, and then those are your solutions. What I know is that this quadratic has, a shape that looks like this. We just graphed 4 minus x squared, so this is going to look something like this. That is just a graph of this picture, not this logarithm. Okay, I'm investigating where this argument is greater than 0. So since this is a parabola that opens up that's been shifted down 4, these points right here are going to be the roots of this function, which is going to be, x minus 2x plus 2. So we're going to have a negative 2 and positive 2. So this will be negative 2, this will be positive 2. So the spots where this thing is greater than or equal to 0 is going to be on these outer tails. So that means its domain is going to look like this. We're going to have negative 2, we're going to have positive 2, and this is strictly greater than 0. So instead of these things being closed, they're actually going to be open because we're not allowed to be equal to 0. So it's here, and then it's going to just be these, positive parts. So I'm talking greater than 0. So it's going to be this part over here and this part over here. What's cool is this logarithm actually looks like this is what happens here, and these are the vertical asymptotes. We'll get to graphing three-dimensional functions, and we'll look at the graphs of two-dimensional functions alongside of those so they look familiar. We'll take a very similar approach. Okay, so when I want to graph the domain of this thing, well, we have a very similar problem. I have a logarithm. Now, the coefficient didn't matter. That's just a vertical stretch. The only thing that we care about is the argument of the logarithm. So again, the argument has to be greater than 0, which means x squared plus y squared minus 9 has to be greater than 0. Now, this is the case to where, like, hey, I see a circle here. I see an x squared plus y squared, so I'm going to go ahead and isolate that. So x squared plus y squared has to be greater than 9. So looking at this thing, I know that I know how to graph x squared plus y squared is equal to 9. I see a circle, like I said, and remember that we're going to have to do a dotted line because this is strictly greater than. So this is a circle of radius 3. X squared plus y squared equals 3 squared. And we're going to do a dotted line because, again, it's strictly greater, so it's going to look like this. If it had an equal sign on there, then we'd put an equals. What I mean by that is if this was a square root instead of a logarithm, this would be solid. Okay. And then it has to be greater than 9, so that means it's going to be outside of the circle. It's going to be bigger than that. And I'm trying to get you guys to see the familiarness of this. That do you see that it's everything outside of this, outside of this radius, very similar to here. It's everything outside of this radius. So if you pick any number inside this shaded region and plug it into this function, it'll give you a real number back. So if you like the videos, please subscribe. Thank you.